Okay, so our next topic in the course is fluid mechanics. So we're moving on beyond or past thermodynamics into fluid mechanics. And the first topic within the subject of fluid mechanics we cover is fluid behavior at interfaces, and that's kind of a fancy way of talking about the idea that what we're really interested in most of the time is how fluids interact with some object or some object that we are actually interested in, right? So say we're building a structure like a building or a bridge or something like that. We may be interested in how the wind, say, interacts with it, like what sort of loads would the wind impart on our building. And so you'd have to design for that. You'd have to be able to, your building would have to be able to withstand whatever loading the fluid would impart upon it. Or maybe we have something a little bit more straightforward. We have an airplane, and its primary purpose is to fly. So its primary purpose is to interact with the fluid in such a way that it can generate lift and move from place to place efficiently, things like that. Or same thing for boats. But so I said all that to sort of illustrate the point that what we're usually interested in is the object that's interacting with the fluid, not necessarily the fluid itself. This isn't always the case, but generally speaking. And the way fluids interact with an interface is called basically the no-slip condition. Okay, and what that is, it describes the fact that when a fluid interacts with a surface, it assumes the velocity of the surface. Okay, so what I have here illustrated is a what's called a velocity profile. So U of y is called a velocity profile. All right, and initially it's a constant profile. Right, so I have a constant velocity approaching a plate. So if a fluid moving in a uniform velocity, so everywhere in space that has the same value. I use the component u because u is the x component of velocity. Like the velocity vector is described as u times the unit normal, the unit vector in the x direction, plus v times the unit vector in the y direction, plus w in the z direction. So u is the x direction, and we set up our coordinate system so that x is parallel to the primary direction of flow usually. Okay, and then in this coordinate system, y is the distance from the surface, and then z is the third direction. So I have a uniform fluid approaching an object or a surface, in this case a plate, at a uniform velocity. And so the velocity is not changing as a function of space. As it interacts with the plate, the fluid in contact with the plate assumes the velocity of the plate. So if this is where if I describe that as y wall, which in this case is where y equals 0, right? So the x direction, or so the velocity evaluated at the y value at the wall equals the the velocity of the wall. So in this case, u of 0 equals 0, right? Because the wall is not moving. This plate is stationary. So u of 0, y wall, happens to be 0, and the velocity of the wall is 0. So in contact with the plate, they assume the same same velocity. And as we move away from the plate, you have this something a little bit more interesting, what's called the velocity profile. This is the velocity profile. It's the x component of velocity as a function of the distance away from the plate, given by the y variable. So we have this function of y, which describes the x component of the velocity. And so it starts at, in this case, 0, and moves, and increases in velocity until back up as we approach infinity. As we approach very far from, as we get very far from the plate, the velocity approaches this value u infinity with which it approached in the first place. Okay. All right, so this is a velocity profile. This region within the velocity profile, roughly that thick, is what's called the boundary layer. Okay, so it's this value, it's this region in here. And so if I zoom in on that, I got something like this. This is where the velocity is changing abruptly, or and it's this distance here is given the value, or given the symbol delta, and so this is the boundary layer thickness. And typically it's defined by the fact that u at delta is equal to 99% of u infinity. Okay, so it's the region closer to the wall than the point at which the velocity is 99% of the velocity very far from the wall. And it usually assumes this is kind of a typical shape of the profile, right? Now, essentially the primary characteristic of a fluid is that it can't support what's called shear stress. All right. Like if I apply a shear stress to a fluid, it deforms continuously. And the sort of the characteristics of how that deformation and how that relation between shear stress and deformation occurs is related to this property called viscosity. All right. So if I have my velocity profile in contact with the plate, there's this, at every point along this, there's a slope. Okay, so this would be du dy, right? The slope of this curve at any point is just the derivative of the x component as a function of y. Usually of interest is where this gradient interacts, where this right here at this interface between the fluid and the wall, this gradient so it's just the typical gradient, but evaluated at y equals the value at the wall. All right, and this gradient creates a force. Which is essentially a shear stress acting on a given area. Okay, so per unit area, the shear stress is defined by uh, this relationship. Okay, and then at the wall, I just evaluate this gradient at the wall. All right, so shear stress or shear force is just the shear stress times a relevant area. Okay, and the shear stress is given by this relationship. So this relationship is what defines a property called viscosity. So for this symbol mu is called the dynamic viscosity. Okay, and the units of u, or the dimensions of u are, or I'm sorry, mu, of the dimensions of dynamic viscosity is Pascal seconds. Okay, or this is equivalent to kilograms or meters times seconds. These two units, these sets of units are equivalent. So the shear force has units of newtons. Shear stress has units of pascals, or so it's got the same units as pressure, but it's in a shearing, what's called essentially a shearing direction. A pressure applies force in a normal direction. Shear stress applies force in a shearing direction. Okay, so the friction between your two hands in this particular case is an instance of shear. All right. I guess just for completeness sake, the units of du, dy work out to be 1/seconds. So in most cases, in most fluids you're familiar with, water, for instance, air, sort of typical fluids, this value mu for the dynamic viscosity is independent of shear stress. All right. So when the viscosity is independent of shear stress, you have what's called a Newtonian fluid. All right. So a Newtonian fluid is defined as a fluid in which the viscosity is independent of shear stress. There are fluids, non-Newtonian fluids, which this is not the case. Things like you have two non-Newtonian. So non-Newtonian fluids come in two varieties. So you have shear thickening, and these would be things like toothpaste, that stuff, oobleck, stuff like that, where essentially, if I apply a shear force to it, it becomes thicker. It behaves as if this viscosity has increased greatly. So, like, you can find videos, and I'll post a couple non-Newtonian videos, sort of describing non-Newtonian fluids. That I'm just going to pull them off of YouTube, but they show this behavior. So with, like, say, oobleck, you have that situation where if you like, say, if you dip your hands into it slowly, or if you interact with it in a slow way, then it behaves like a fluid. It behaves as if this viscosity is fairly low. But if I punch it, it responds as if, almost as if it were a solid. So what happens is that this viscosity is a function of the shear stress that I apply. That's another way of looking at it, anyway. And so the viscosity greatly increases with the function of the shear stress. And then you have things like shampoo or blood. And these are examples of shear thinning fluids. And I'll show some of those as well. So shear thinning fluids, if I apply a shear force to it, they become less viscous. But typical fluids that we're going to deal with are neither of these, and this is a constant. All right. And so things like water and air, the viscosity of those fluids, water, air, most gases, that sort of thing, if not all gases, I'm not sure, are independent of the shear stress. And so this, as for the most part, it can be treated as a constant. Viscosity is, however, in both gases and liquids, in Newtonian fluids, usually a pretty strong function of temperature. With liquids being on the order of 10 to the -3 in these units. And as a function of temperature, they tend to be, the viscosity drops as a function of temperature. And this is for liquids. However, for gases, even though they're much less viscous, their viscosity tends to increase with temperature. Okay, and this is not to scale, obviously. The phenomenon. So this is a general sort of general fact. I mean, maybe a fact or an observation, but the relationship between these two is kind of interesting. So for liquids, you have a situation where the molecules themselves are fairly close together. You know what I mean? And so if they're interacting with a surface, the molecules close to the surface are going to be moving slow. However, the molecules far away from the surface are moving much faster. And at lower temperatures, they're in close contact with each other, right? And so their motion is somewhat inhibited. At higher temperatures, they're able to spread out a little more. The increased thermal energy imparts this random vibration to random fluctuation, I guess, to the velocity of each one of these things in such a way that they make space for themselves, and now they're able to flow more effectively past one another, right? They're just kind of rolling on top of each other. Now they have more space to do it. So this is for liquids. And so as a function of temperature, the viscosity is shown to decrease. All right. Then for gases, you already have a situation. They begin this state where they are very well spaced out, right? And say they're interacting with this surface, and so you have faster moving molecules at the top and slower ones closer to the surface. All right, and then as temperature increases, you have these slower moving molecules in close contact with the surface. But now this random fluctuation in their velocity imparted by the additional thermal energy gives them the ability to jump up here and interact with faster moving particles. So these molecules further away would normally be moving much faster, but the ones that are down here are now able to they're able to fluctuate up in such a way that they're bumping into it, or they're interacting with these molecules that would otherwise be going faster. So what happens is these slower molecules are able to jump up here, bump into the faster ones. So the faster ones get slowed down, but the slower ones get sped up a little bit. You know what I mean? So there's momentum transfer toward the wall. So these molecules up here would have higher momentum, but because of this, they're able to interact more freely with the ones closer to the wall. These slower moving molecules, momentum is sort of transferred towards the wall a little bit. And so this is what happens for gases. So this momentum transfer increases the viscosity for gases as a function of temperature, and decreases for and this other phenomenon kicks in for liquids. But they're still not comparable directly as far as their absolute, the value of viscosity. Gases tend to be much lower viscosity than liquids in normal situations.